before doing the problem, we shall just see a molecular chart. This curve is the saturation curve. So this region is the wet region, and the region above is the superheated region. And you see the dryness fraction lines, dryness fraction 0.9, 5.9, etc. The pressure lines to the top, it moves to the top. This 1, 2, 4, 10, 20 represents pressure. This blue curve, and this green curve represents the temperature. It moves towards the right. So for studying this, you take your molecular chart from your steam table. And the first problem is very simple. A steam nozzle, the steam expands from 4 bar to 1 bar. The initial velocity is 60 meter per second. Initial temperature is 200 degrees Celsius. Determine the exit velocity if nozzle efficiency is 92%. So initial pressure 4 bar, P1 4 bar, final pressure 1 bar, P2 1 bar, and you just that it is a convergent nozzle. And the initial velocity C1 is given. The initial temperature is also given. So you take your molecular charge, and by taking 4 bar 200 degrees Celsius, you will get the 0.1. This 200 degrees Celsius temperature curve, 4 bar pressure curve. The intersection is 0.1, and that point is in the superheated region. So condition 1 is superheated condition. And you take the enthalpy value from the y-axis, it is 2860 kilojoule per kilogram. And if it is assumed as isentropic, the expansion will be a vertical line. It follows a vertical line. So draw a vertical line from 1. And about condition 2, the pressure is given 1 bar. So you just consider the 1 bar pressure line. And the intersection of this 1 bar pressure line and the vertical line drawn from the state 1 is your point 2. So this meeting point is 2. So I got 2. Correspondingly, the enthalpy from y-axis is 2605 kilojoules per kilogram. Now, H1 and H2 are given. You know the expression for nozzle efficiency, that is H1 minus H2 dash by H1 minus H2, and by substituting values of H1, H2 and nozzle efficiency, you will get H2 dash, or you will get the actual enthalpy drop H1 minus H2 dash. And here the inlet velocity C1 is given, so you follow the first equation, H1 plus C1 square by 2 equal to H2 dash plus C2 dash square by 2. If it is 1 dash, you take the conditions as H2 dash C2 dash. And by taking H1 minus H2 dash, and this value is to 34.69 kilojoules, and you convert this kilojoule to joule, that is why here multiply by 10 raised to 3, you will get the exit velocity C2 dash. So I considered 1 2 dash because the nozzle efficiency is given in the problem. If the nozzle efficiency is not given, you can take it as isentropic 1 2. There is no need to consider the point 2 dash. So it is a straight away problem. Just try to do this by using your molecular chart. And second problem, it is given that dry-saturated steam at a pressure of 11 bar enters a convergent divergent nozzle and leaves at a pressure of 2 bar. And the flow is adiabatic and frictionless. Determine exit velocity, the ratio of cross section at exit and that at throat. So it's a convergent divergent nozzle. But it is given that the flow is adiabatic and frictionless. Adiabatic and frictionless means isentropic. So the condition 1 is dry saturated at pressure 11 bar. If it is dry saturated, the index of expansion is 1.135. And the exit pressure is given. Exit pressure is P3, 2 bar. And you just note that the inlet velocity C1 is not given. And we can go for finding the throat pressure by using the expression for critical pressure ratio. P2 by P1 is 2 by n plus 1 the whole raised to n by n minus 1. N is 1.135. So this gives the throat pressure as 6.38 bar. So you take your molecular charge. The condition 1, dry saturated. So it is on this curve. Pressure is 11 bar. So 11 bar pressure on saturation curves gives you a 0.1. Corresponding enthalpy is 2780 from y-axis. Then two more pressures are known. the throat pressure P2, the exit pressure P3, 6.38 bar and 2 bar respectively. So you consider these two pressure curves in your Molière chart, and the flow is isentropic. So just draw a vertical line from 1, the meeting point with 6.38 bar pressure curve is 0.2, the meeting point with 2 bar pressure curve is 0.3. So you will get 0.2 and 3, get the enthalpy values from the y-axis, and also you note down the dryness fraction values. Dryness fraction values from the Molière chart. X2 is 0.96, X3 is 0.9. And for getting the specific volume of wet steam or equation, we know V equal to Vf plus X Vfg. Vfg is Vg minus Vf, and this Vf is volume of vapor, and Vf is volume of liquid, and Vg is the volume of vapor. The volume of liquid is very, very small, negligible when considering the volume of vapor. So Vf is very, very small when considering Vg. So Vf can be neglected. So this V is X Vg only. By neglecting Vf, the specific volume of wet vapor is X Vg. So you take throat, the enthalpy X2 you got from Molière chart, and the throat pressure is 6.38 bar. And for getting V2 is Vg2. For getting Vg2, you take your steam table and find Vg at 6.38 bar. This value should be approximated. Maybe 6.38 may not be there in your steam table directly, but you approximate the value so that Vg at 6.38 bar is taken. It is taken as 0.297 meter cube per kilogram. So these two are from Molière chart, this from steam table. So velocity is not, inlet velocity is not given, so you can use this equation. C2 is 44.72 root of h1 minus h2. This gives the throat velocity, and V2 is x2 Vg2, and the equation for m dot is AC by V. So m dot is A2 C2 by V2. This thing we studied in thermodynamics, mass flow rate m dot. And this V2 is x2 Vg2, and by substituting the values of C2, x2 and Vg2, your A2 becomes m dot into 0.000634. And similarly for exit, X3 from Molière chart, you already got it. The pressure is 1.05 bar, or sorry, 2 bar, pressure is 2 bar. So Vg is Vg at 2 bar, 0.885 meter cube per kilogram. This value will be there directly in the table, from steam table. And the exit velocity C3, inlet is not given, so it is 44.7 root of h1 minus h3. C3 is calculated. M3 is A3 with C3 by V3. V3 is X3 Vg3, and by substituting C3 and C3, X3 and Vg3, your A3 is 0.001028. Your question is the ratio of exit to throat area. So it is A3 by A2. Substitute these values, A3 here, A2 here. The ratio you got as 1.62. So here the expansion is isentropic. Convergent divergent nozzle with isentropic expansion. And the next problem, a convergent divergent nozzle is given. Steam initially at 14 bar and 80 degrees Celsius to superheat. Here it is degree of superheat is given. Temperature is not directly given. Instead of that, degree of superheat is given, where it is expanded to a back pressure of 1.05 bar. Back pressure is the exit pressure, P3. For us to find the throat and exit diameters, the mass flow rate is given. Steam discharge is 500 kg per hour, that is mass flow rate. Assume that the expansion is in thermal equilibrium throughout, and the friction reheat amounting to 12% of total enthalpy drop to be effective in the divergent part of the nozzle. So the effect of friction is only in the divergent part of the nozzle, and the friction reheat is equal to 12% of total isentropic enthalpy drop. Total isentropic enthalpy drop is h1 minus h3. So these are the given values. And degree of superheat is the difference between superheated temperature and saturation temperature. So you take your steam table, find the saturation temperature at 14 bar, Tsat at 14 bar, it is 195. So Ts is Tsoup minus Tsat. Ts is given as 80, Tsoup is your T1, Tsat is 195. So you can find T1. T1 is calculated, 275. P3 is 1.05 bar, and by taking 275 and 14 bar, it is find that